Hello, everyone. In this class, we will study the basic concepts of rebar detailing in standard structural drawings. We will explain from the following aspects. 1. Types and symbols of rebars. 2. Thickness of concrete cover. 3. Rebar anchorage and 4. Rebar connections. First, the grades of rebar. Rebars commonly used in engineering are classified as grade 1, 2, 3 and 4 steel. In the Code for Design of Concrete Structures and 1/6 G101 standard drawings, rebars are classified into 4 grades: HPB 300, HRB 335, HRB 400, and HRB 500. Each grade of rebar has corresponding representation symbols, as shown in the table. You should recognize these rebar signs. In rebar grade designation, H stands for hot rolled, P stands for plain, R stands for ribbed, and B indicates bar. The numbers after these letters represent the yield strength. For example, in 3Phi20, 3 indicates there are 3 rebars. Phi represents grade 3 steel HRB 400, and 20 indicates the rebar diameter. Another example is Phi8 at 200. Phi indicates grade I steel. 8 indicates the diameter is 8 mm. At is the equal center-to-center spacing symbol. And 200 means the spacing between adjacent rebars is 200 mm. The second part we'll discuss is concrete cover. The exposed rebars are prone to corrosion. Thus, rebars need a certain thickness of concrete protection, which is called concrete cover. Its functions include: first, enhancing the bond between rebar and concrete. Second, protecting rebars from corrosion to ensure the concrete durability. Third, preventing premature softening of rebars in case of fire incident. Using the beam reinforcement as an example, concrete cover thickness refers to the distance from the outer edge of stirrups to the concrete surface. The thickness shouldn't be too thin nor too thick. The thicker the concrete cover, the better the bond and anchorage performance, durability, and fire resistance of structural members. However, excessive cover thickness will cause excessively wide cracks when the member is loaded, affecting its serviceability and causing economic waste. Therefore, in the Code for Design of Concrete Structures, the minimum concrete cover thickness is specified, as shown in the table. For Class I environment, the minimum concrete cover for slab and wall members is 15 mm, while that for beams and columns is 20 mm. As the environmental category increases, which indicates environmental conditions worsen, the required minimum concrete cover thickness gradually increases. Additionally, the minimum cover thickness for beam members is greater than that for slab members. The foundations are below ground, where it's relatively humid. Thus, the concrete cover thickness for foundation rebars should be measured from the top of the blinding layer, and the length should be not less than 40 mm. Now, let's proceed to the third part: rebar anchorage. In construction, we often encounter the issue of reinforcing bars being anchored into supports. So how do we determine anchorage length? For example, In our real life, when two teams are in a tug of war, is a longer rope or shorter one better? Clearly, with a longer rope, it's easier to grip and requires more force to pull the rope from hands. Similarly, rebar anchorage follows the same principle. Anchorage length refers to the length required for rebars anchored in supports to rely on surface bond with concrete to reach the design stress. The 1G101 standard drawings specify basic anchorage lengths under non-seismic and seismic conditions are denoted as lab and labby respectively, and anchorage lengths under non-seismic and seismic conditions as La and Lay respectively. Basic anchorage length refers to the theoretical minimum anchorage requirement, while anchorage length considers practical conditions. As shown in the table, for seismic design, tensile rebar anchorage length Lay closely relates to rebar type, concrete strength grade, seismic level, and rebar diameter. From the table, we can see that the higher rebar grade corresponds to the longer anchorage length and the higher concrete strength grade, while the shorter anchorage length corresponds to the higher seismic level and the longer anchorage length. For example, in Grade 3 seismic frame beams with concrete strength Grade C30, Grade 3, 20 mm diameter tensile rebars, what's the seismic anchorage length? By checking the corresponding seismic tensile rebar anchorage length table. Grade 3 steel, seismic Grade 3, concrete Grade C30. We can see that the diameter is less than 25 mm. So the anchorage length is 37 d, where d is the rebar diameter. Therefore, for this frame beam, the seismic anchorage length is 740 mm. Now let's proceed to Part 4, rebar connections. In construction, when rebar length is insufficient, we need to connect rebars. There are three connection methods: lap splicing, welded connections, and mechanical connections. In building construction, slabs and beams commonly use lap splicing. For column rebars with diameter less than 12 mm, lap splicing is generally used. For diameters between 12 to 25 mm, welded connections should be used. And when the diameter exceeds 25 mm, coupler mechanical connections are adopted. When using lap splicing, rebars must meet lap length requirements. If lap length is too short, it won't meet load-bearing requirements, while too long rebar wastes materials, so lap length must be appropriate. The 1G101 standard drawings provide tables for longitudinal tensile rebar lap length L_I and longitudinal tensile rebar seismic lap length L_IE. In the longitudinal tensile rebar lap length table I_I, we can see seismic lap length depends not only on rebar grade, concrete strength and diameter, but also on the percentage of lap splice in the same zone. Now, please think about this question. What is the percentage of lap splice in same zone? First, same zone refers to a certain length range for longitudinal rebar connections. For lap splicing, It's 1.3 times the lap length, as shown in the diagram, assuming that the diameters are equal. And there are 4 parallel rebars in this zone, with 2 lap splices, so the percentage is 50%. For mechanical connections, the same zone length is 35D. And for welded connections, it's the greater length of 35D or 500 mm. When connecting rebars, connections should be in low-stress areas and must be staggered. Within the same zone, connection percentage must meet requirements. Everyone, in this class, have you learned to determine lap length for longitudinal tensile rebars? Let's try an example. In a grade 3 seismic structure, slab rebars use lap splicing. And in the same connection zone, splice percentage is 25%. Determine lap length for Phi 8 rebars in C25 concrete slab. First, locate grade 3 seismic in table. And then find grade I steel HPB300. Splice percentage is 25%. Concrete strength is C25. From table, we get that lap length is 43D, meaning 43 multiplied by 8 equals 344. So the lap length should be 344 millimeters. Today, we learned rebar basics, rebar grades, concrete cover, anchorage, and connections. In the following courses, you will need to apply these knowledge. Please make sure you have a solid understanding. That's all for today. Goodbye.